There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. Now, if you appreciate this and don't take the lecture too seriously, that you really have to understand in terms of some model what I'm going to describe, and just relax and enjoy it, I'm going to tell you what nature behaves like, and if you will simply admit that maybe she does behave like this, you will find her a delightful...
Imagine that you're a physicist the size of a protein living inside a cell. The first incarnation of your life is a motor protein called Kinesin. Unfortunately, you live a boring and laborious life. All you do is drag a cargo along a microtubule. The size of your steps matches the size of tubulin subunits, the building blocks of microtubules. Your walking motion is powered by the hydrolysis of ATP. Each of your steps is coupled with the breaking of one phosphoanhydride bond of ATP. You always advance one step at a time. Each step is an atomic action, and no partial step can be taken. As far as you know, you've been walking non-stop for your whole life. When you look around, you see a complex network of microtubules and protein filaments. A host of motor proteins are busy moving their cargo to different destinations. Once in a while, millions of mindless particles spontaneously gather together and form this superstructure. They work in synchronization, and dividing two copies of identical chromosomes with a high precision. This project is reliably being done numerous times inside many living organisms on the Earth. The scale and complexity of the project makes building the Large Hadron Collider look like a trivial task. Marveled by what you've accomplished, you and your fellow movers try to figure out what laws of physics govern the motion of objects in your world. You're pretty sure your motion has nothing to do with any of the fundamental forces concocted by human physicists. The so-called gravitational force is too weak to have any impact on you. The strong and weak forces act only at subatomic distances. They cannot have any direct effect on your walking motion. The electric force might remotely explain the binding between you and your cargo, but it definitely does not cause your walking motion. In fact, you and your fellow movers always walk at a steady pace on a microtubule, and never experience any acceleration or deceleration. The whole concept of force, inertia, and mass makes no sense to you. The laws of Newtonian physics are hopeless in explaining your walking motion. You have to develop your own physics from the ground up. Inside a cell, there are many similar step motors responsible for a variety of biological processes. These molecular machines differ in shapes and sizes, but the motion of these objects share one prominent feature. They all advance one step at a time on a linear path. Each step corresponds to a repeated working cycle, and each cycle contains a series of discrete actions. In other words, your universe operates quantum mechanically. A quantum here means an atomic action. Quantum mechanics just means that the operation of your universe is transactional, and it executes one action at a time. For now, your universe is a mechanical system that behaves deterministically. No one plays dice with the system. The system doesn't display any weird quantum behavior such as superposition and entanglement. Without loss of generality, let's look at such a quantum system with two interacting particles. This symbol represents a kinesin, and this line represents a microtubule. When a kinesin binds to a microtubule, it produces distinct walking motion. The walking motion is the result of a series of particle interactions. Each walking step is an atomic action, denoted by letter h. This defines the fundamental unit of measurement for this particle interacting system. A microtubule defines a path on which a walking kinesin can move. The action of a path, denoted by letter s, is the number of steps taken by a kinesin along the path. The physical quantity s measures the length of a path in the unit action h. The unit action h can be modeled by a unit circle. A dot moving on a unit circle represents a kinesin walking along its path. The area of one unit circle represents one step walked by a kinesin. When a dot moves on a unit circle, the arrow connecting the center to the dot rotates around the circle. The area swept by the rotating arrow is proportional to the amount of steps walked by a Kinesin. When a Kinesin walks a full step, the arrow draws a complete circle. When the Kinesin walks another step, it draws another circle. To generalize it, a rotating arrow models the execution of a unit action in a quantum system, and the area swept by the arrow tracks the amount of actions executed by the system. To model a large system with lots of different step motors, we draw a rotating arrow for each and every step motor in the system. For slow-moving motors, we draw slow rotating arrows. For fast-moving motors, we draw fast rotating arrows. For motors moving in the opposite directions, we draw arrows rotating in the opposite directions. For a group of motors moving at the same speed, we draw a long arrow so that the area swept by the arrow per unit time is proportional to the number of steps walked by the group during the same period of time. At the end, we add all rotating arrows together, tip to tail. The combined arrow will create some unique pattern. The pattern represents the collective behavior of the combined system. Imagine that we draw rotating arrows for all motor proteins inside our body. The resulting pattern fully describes everything that we do in our life. To understand the laws governing the process of pattern creation, we need a better way to represent an enormous number of rotating arrows. A rotating arrow points to a unique point on a unit circle. The point is mapped to complex number phi. Phi equals e to the power of I theta, where theta is the angle swept by the arrow. Complex function phi of theta models a rotating arrow around a unit circle. We can create a similar function to model the motion of a walking Kinesin. A full step of a walking Kinesin is 1 unit of action h. A complete revolution of a rotating arrow is 2 pi radians. In this representation, the amount of action s, measured in the units of h, is equal to the angle theta, measured in the units of 2 pi radians. Move constant h and 2 pi to the right side of the equation. We get this formula which converts angle theta to action s. Let h bar denote the conversion factor h divided by 2 pi. This equation shows that the action s equals the angle theta time h bar. Rearrange the equation. This shows how to convert action s to angle theta. Theta equals s divided by h bar. Combine the conversion formula with phi of theta equals e to the I theta. Complex number phi is now expressed as a function of action s. Phi of s equals e to the power of I times s divided by h bar. Group the constant I and h bar in the exponent, and substitute s with the actual value. We deduce the complex function that models the state and evolution of a quantum system. If you're unfamiliar with complex number, you might feel completely lost right now. What does it really mean by raising e to the power of an imaginary number? Why do we want to use complex function to describe the behavior of a quantum system? Don't worry. You'll learn all the maths required to become a theoretical physicist in 5 minutes. Let's answer the first question first. What does it really mean by raising e to the power of an imaginary number? A complex number phi is usually written in standard form, a plus bi, where I is the square root of -1, the imaginary unit. Each complex number can be mapped to a unique point on complex plane. The real part of the complex number corresponds to the x-coordinate of the point. And the imaginary part of the complex number corresponds to the y-coordinate. Connecting the origin to the point creates an arrow. This is the arrow represented by the same complex number. The length of the arrow r equals the square root of a square plus b square. The length of the arrow r is the modulus, or the absolute value of a complex number. The real part of a complex number equals r cosine theta, and the imaginary part equals ri sine theta, where theta is the angle between the arrow and the real axis. Therefore, the same complex number can be expressed in trigonometric form, r cosine theta plus ri sine theta. According to Euler's formula, e to the I theta equals cosine theta plus I sine theta. Substitute cosine theta plus I sine theta with e to the I theta. The same complex number can be expressed in exponential form, r times e to I theta. The three different forms represent the same complex number. In our discussion, we often use the more compact exponential form. The next question is, why do we want to use complex number to describe a quantum system? To understand why, we need a basic understanding of the arithmetic of complex numbers. Suppose that there are two complex numbers, phi1 equals the square root of 3 minus 1i. Its absolute value is 2, and its angle is theta 1, which equals negative 1/6 pi radians, or 30 degrees clockwise. Phi2 equals 2 plus 2 the square root of 3i. Its absolute value is 4, and its angle is theta 2, 1/3 pi radians, or 60 degrees counterclockwise. Adding two complex numbers is to add their real parts, and then add imaginary parts. The sum of phi1 and phi2 is a new complex number, corresponding to this red dot. The addition can be done by adding two arrows. For example, to add arrow phi1 to arrow phi2, draw phi1 from the tip of phi2. The resulting arrow now points to the sum of phi1 and phi2. The operation of adding arrows is commutative. To add phi2 to phi1, draw arrow phi2 from the tip of phi1. The resulting arrow also points to the sum of phi1 and phi2. To better understand the multiplication of two numbers, let's rewrite phi1 and phi2 in the exponential form. The product of phi1 and phi2 is computed by multiplying these two numbers. Rearrange the terms and combine the angles in the exponent. The algebraic expression tells us that multiplying two complex numbers is to multiply their absolute values and then add their angles. These two operations correspond to scaling and rotating arrows. For example, to multiply phi1 by phi2 is to scale arrow phi1 by 4, the absolute value of phi2, and then rotate the scaled arrow by 60 degrees counterclockwise, the angle of phi2. The resulting arrow points to the product of phi1 and phi2. The operation of scaling and rotating arrows is also commutative. To multiply phi2 by phi1, scale phi2 by 2, the absolute value of phi1, and then rotate the scaled arrow by 30 degree clockwise, the angle of phi1. The resulting arrow points to the product of phi1 and phi2. Adding complex numbers is to add arrows. Multiplying complex numbers is to rotate arrows. That's all the math a theoretical physicist needs to know in the world of kinesins. Next, let's see why the algebra of complex numbers is the natural language for describing the state and evolution of a quantum system. As discussed before, a rotating arrow models the motion of a walking kinesin. Therefore, a walking kinesin can be represented by a single complex number corresponding to the rotating arrow. Instead of saying, the initial state of the system is one kinesin at position S0, we can translate this statement in English to an equation, phi0 equals e to the I2 pi 0. Or, we can express the statement as a complex function, phi of s equals e to the I over h bar times S0. Instead of saying, the system advances one step, and evolves into a new state, we use the equation, phi1 equals phi0 multiplied by e to the I2 pi. Or we can express the evolution of the system as a recursive function. The value of phi of s is updated with its previous value multiplied by e to the I2 pi. The complex number, e to the I2 pi, represents an action executed by a quantum system. E to the I2 pi has the absolute value of 1, and the angle of 2 pi radians. When it multiplies a complex number representing the state of a system, it doesn't change the length of the arrow, hence the area swept by the arrow. This stands for the total amount of particles in the system remains unchanged. The multiplication rotates the arrow by a full circle. This means, after completing one cycle of evolution, the system returns to a state ready to start a new cycle. To compute the new state of the system, solve this equation representing the evolution of the system. The result is complex number phi1, e to the I2 pi 1. Translate this equation back to a statement in plain English. It says, the new state of the system has one kinesin at position S1. This accurately describes the new state of the system. Microtubules are polar structures with two distinct ends, a fast-growing plus end and a slow-growing minus end. The underlying mechanism determines that motor proteins travel a specific direction along a microtubule. Kinesins always walk from the minus end to the plus end. Let phi plus denote the system in which kinesins walking toward the right, and phi minus denote the system in which kinesins walking toward the left. A step to the right corresponds to an arrow rotating counterclockwise, represented by complex number e to the plus I2 pi. The evolution of the plus system can be expressed as multiplying its state phi plus by the complex number representing a step to the right. Similarly, a step to the left corresponds to an arrow rotating clockwise, represented by complex number e to the minus I2 pi. The evolution of the minus system can be expressed as multiplying its state phi minus by the complex number representing a step to the left. The state of a composite system with microtubules pointing to both directions is represented by the sum of phi plus and phi minus. The evolution of such a system is expressed as multiplying the state of subsystem, phi plus and phi minus, by e to the plus I2 pi and e to the minus I2 pi, respectively. This equation can be expressed in a shorthand form. Phi of s equals phi of s times e to the plus and minus I2 pi. A pair of complex conjugates, e to the plus I2 pi and e to the minus I2 pi, represents a pair of action and counteraction in a quantum system. The equations expressing the state and evolution of a composite system have the same form as those expressing the state and evolution of the most simple system with just one kinesin walking on one microtubule. Let's look at a concrete example to see how the algebra of complex numbers describes such a composite system. Suppose that there are two kinesins on the microtubule pointing to the right. One is at position S1, and the other at position S2. On the microtubule pointing to the left, there are also two kinesins. One is at position S3, and the other at position S4. Apply a pair of action conjugates to the complex numbers representing individual kinesins. The positive conjugate, color-coded in red, increases the exponent of the two complex numbers in red. The change in red numbers corresponds to the two red kinesins walking right. The negative conjugate, color-coded in green, decreases the exponent of the two complex numbers in green. The change in green numbers corresponds to the two green kinesins walking left. The complex representation not only tracks the relative position of kinesins on both microtubules, but also computes other important physical quantities in the system. The area swept by rotating arrows is proportional to the action executed by the corresponding system. The plus and minus signs signify two opposite systems. One system produces positive actions, corresponding to steps walked by red kinesins. And the opposite system produces negative actions, corresponding to steps walked by green kinesins. When the amount of actions equals the amount of counteractions, they cancel out each other, and the center of the combined system doesn't move. The arithmetic of complex number models the state and evolution of a composite system very well. The tubulin subunits of different microtubules may not be aligned perfectly. The shift between a microtubule and a frame of reference is expressed as the length of the frameshift delta s measured in the units of h, or an angle in the units of 2 pi radians. A frame shifted x step forward has the same effect as a frame shifted 1 minus x step backward. In our discussion, we'll use a principal angle between -1 pi and +1 pi to represent the degree of the frameshift. For example, this microtubule shifts 1/6 of a step forward relative to the frame of reference. The degree of the frameshift is 1/6 of 1 unit length h, or 1/6 of 2 pi radians. Simplify the value in radians. The frameshift on this path is θ1, 1/3 pi radians, or 60 degrees. This second microtubule below shifts 1/12 of a step backward. The frameshift on path 2 is θ2, -1/6 pi radians or -30 degrees. A kinesin at position S2 on path 1 is at position θ1 plus 2 pi 2 relative to the frame of reference. The kinesin is represented by complex number e to the I times θ1 plus 2 pi 2. Similarly, a kinesin at position S4 on path 2 is at position θ2 plus 2 pi 4 relative to the frame of reference. The kinesin is represented by complex number e to the I theta 2 plus 2 pi 4. A kinesin on path 1 is mapped to a point on the unit circle with a phase angle of theta 1. A kinesin on path 2 is mapped to a point on the unit circle with a phase angle of theta 2. If there are more than one kinesins on a particular path, we add up all complex numbers to compute the sum representing the state of the system on the path. The state of the subsystem on path 1 is always mapped to an integer point on the radius line with a phase angle of theta 1. The state of the subsystem on path 2 is always mapped to an integer point on the radius line with a phase angle of theta 2. To generalize it, a kinesin at position Sn on a microtubule with a frameshift of theta k is represented by complex number e to the I theta k plus 2 pi n, where theta k is a principal angle between negative pi, and both k and n are integers. For a given microtubule k, the frameshift theta k remains constant during a walking session. So, e to the I theta k is a constant. The kinesin at position Sn on microtubule k can be expressed as phi of Sn multiplied by constant e to the I theta k. The state of the subsystem for each path is represented by a set of discrete integer points. The integer points are located where the corresponding radius line intersects with a series of concentric circles. For example, 3 kinesins walking on path 1 corresponds to the point on the radius line with a phase angle of theta 1 and an absolute value of 3. 2 kinesins walking on path 2 corresponds to the point on the radius line with a phase angle of theta 2 and an absolute value of 2. The state of the combined system is the sum of all subsystems, represented by this orange point. The evolution of the combined system and individual subsystems is expressed by multiplying their states by 2 to the I2 pi. The multiplication causes the corresponding points to move around circular orbits on the complex plane. These circular orbits represent some stable states in an ever-evolving quantum system. They are not the same as the actual orbits traveled by particles in a physical system. We shall not make such a conceptual mistake. When a kinesin moves from path 1 to path 2, the state of the combined system moves to this point. For a system with 5 kinesins on 2 paths, there are 6 possible combinations. It's represented by 6 discrete points on the complex plane. Let's draw a line crossing all points, and label it E5. E5 is associated with a particular rate of ATPs consumed by the system. This can be expressed as E5 equals 5 ATPs per unit time tau. E5 is also associated with a particular number of actions produced by the system. This is expressed as E5 equals to 5 action h per unit time tau. Let's define a physical quantity called energy measured in the units of ATPs. E5 stands for the energy level required to sustain a system of 5 walking kinesins. Imagine that one kinesin falls off a microtubule. The system now contains 4 walking kinesins and 1 free-moving kinesin. There are 5 different combinations in such a configuration. It corresponds to 5 discrete points on energy level E4. The one free kinesin jiggles around and collides with random particles. The Brownian motion of free kinesin is different from the orderly motion of walking kinesins. The free kinesin becomes part of the thermal environment. It doesn't consume any ATPs. The level of energy consumption at E4 is expressed as E4 equals 4 ATPs per unit time tau. At energy level E4, the system produces 4 actions per step. It's expressed as E4 equals 4 action h per unit time tau. We can enumerate all combinations under the configuration of 3, 2, or 1 walking kinesin. We will have similar equations to describe the rate of energy consumption and action production by the system. When no kinesin walks on any microtubule, the system consumes no ATPs and produces no actions. It's just a thermal environment in which the quantum system operates. E0 stands for the base energy level of such a thermal environment. We can combine individual equations in a general form. Energy level En equals the consumption rate of ATPs, or the production rate of action h, where n must be an integer. The equation states that a quantum system must stay at some discrete energy levels. Imagine that a giant physicist the size of the Earth tries to study the encircled system. Because of his size, the encircled system looks like a point particle to him. He has no means to observe tiny kinesins, microtubules, and ATPs directly. The encircled system is to the giant physicist as an atom to a human physicist. Just as a human physicist, he calls the system under study an atom. As far as he can tell, an atom contains large empty space called vacuum. From the vantage point of small human observer who can examine the same system in great details, it's easy to see that his vacuum is actually a chaotic thermal environment. His atom encapsulates a particle interacting system that operates in such an environment. The moving dots shown here are plastic beads attached to kinesins. The beads are a few hundred times bigger than kinesins. They help to trace the motion of much smaller kinesins. When kinesins bump into the binding site of a microtubule, they travel along the microtubule at a steady pace. When they're detached from a microtubule, they undergo random Brownian motion. The whole system is immersed in an ocean of jiggling particles. They constantly bombard each other, roughly at the speed of a bullet. A physical system always operates in some kinds of thermal environment. Any particle interaction, such as a kinesin walking along a microtubule, could be disrupted by a random collision at any moment. The thermal environment causes the uncertainty in all particle interactions. It is the invisible hand that tirelessly plays dice with the universe. Einstein once said that he does not believe God plays dice with the universe. This simple mechanism should settle Einstein's dice problem once and for all. The thermal environment also solves another puzzle that underlies Einstein's theory of relativity. Why is the speed of light constant in all directions, regardless of the speed of light source? It is because the speed of light is a thermal speed. We need to do some preparatory work before we can deduce the result. For now, let's focus on something simple and straightforward. Imagine that we has a special Geiger counter. The Geiger counter clicks whenever it detects an ADP molecule. When kinesins walk on a microtubule, it keeps producing ADPs. The ADPs radiate from the catalytic site of walking kinesins to the environment. Using our special Geiger counter, we'll discover a phenomenon called radioactivity. Because of the thermal environment, the radiation looks completely random to us. It's impossible to predict when and where the next click is. If we carefully measure ADP radiation from an atom of walking kinesins, we should be able to discover discrete energy levels. If we track its ADP radiation level over the time, we will discover that some atoms are stable and others undergo radioactive decay. All physical systems are living systems. They require energy to sustain their operation. If a system of walking kinesins operates in an environment that can replenish its ATP supply like a living cell, the system will radiate ADPs at a sustainable level. If a system operates in an environment without sustainable energy source, more and more kinesins will stop walking. The rate of ADPs radiated from the system will drop correspondingly. The dropout rate is proportional to the current population of walking kinesins, which can be expressed in a differential equation. dN over dt equals minus lambda times n, where n is the current population of walking kinesins, and lambda is the decay rate. Solve the differential equation. The solution explains exponential radioactive decay. If we plot the amount of ADPs radiated from different systems, we can compute their decay rate lambda. Lambda measures the difference between a system's energy production rate and consumption rate. Suppose that there are 5 kinesins in this encircled system. 2 red kinesins bind to one cargo, and 3 yellow kinesins bind to another. Let's assume that the binding is very strong, and kinesins of the same color always move together. When all 5 kinesins are detached from microtubules, the system is at energy level E0. E0 represents the equilibrium state of the thermal background. When 2 red kinesins bind to a microtubule and walk along it, the system jumps from E0 to E2, and consumes 2 ATPs at a time. If we measures the system using a special Geiger counter, we will detect that it radiates 2 ADPs at a time. If the 2 red kinesins fall off, and the other 3 yellow kinesins bind to a microtubule, the system jumps from E2 to E3. When 3 yellow kinesins walk along a microtubule, the system consumes 3 ATPs and radiates 3 ADPs at a time. When all 5 kinesins walk along a microtubule, the system jumps to E5. At E5, the system radiates 5 ADPs at a time. In all possible combinations, the energy is always absorbed and radiated in discrete quanta. The base unit of these quanta is the absorption of 1 ATP or the radiation of 1 ADP. Absorbing an ATP is always coupled with radiating an ADP. It's conceivable that a giant physicist could discover quantum mechanics if he studies walking kinesins from a distance using a Geiger counter. He might also discover another interesting phenomenon called photoelectric effect. The system stays only at E0, E2, E3, and E5. It never radiates 1 or 4 ADPs at a time. When the system is at E3, it doesn't absorb 1 ATP at a time. Instead, it has to absorb 2 ATPs at once, and jump to E5 directly. Similarly, when the system is at E2, it doesn't absorb 2 ATPs. It always absorbs 3 ATPs at once, and jump from E2 to E5. And its behavior can be explained by absorbing or radiating 2 distinct energy packets. One is associated with 2 quanta of ADP radiation, represented by red flashes. And the other 3 quanta of ADP radiation, represented by yellow flashes. If we increase the spatial resolution of ADP Geiger counter, we'll observe that 2 flashing patterns actually travel along 2 different paths. From the perspective of a distant observer, each flashing pattern corresponds to a traveling particle. Note that kinesins, microtubules, and ATPs are not directly observable. When they're not forming a walking kinesin complex, they're part of the invisible thermal environment. If an observer increases the sensitivity of his ADP Geiger counter, he will observe ADP radiation signals like this. The signals are caused by background energy consumption. Usually, people think these are not real signals but white noises. When they fine-tune the sensitivity of their instrument, signals emerge from background noises. Each unique flashing pattern represents a distinct particle. For a distant observer with only a Geiger counter, these particles seem to travel in empty space, just as a human observer sees that photons travel in vacuum. Imagine that we quickly swap a group of 3 yellow kinesins with another group between 2 steps. A distant observer with a limited visibility wouldn't notice the swapping. He would see that the same yellow particle continues moving forward. If we remove 1 kinesin from the yellow group, the observer would notice that the old yellow particle disappears, and a new red particle shows up. Therefore, the particle detected by Geiger counter is not tied to any particular kinesins, ATPs, or tubulin subunits. A traveling particle is a continuous particle interacting system that co-moves in a chaotic thermal environment. Particles are not defined by their individual parts but by the actions that create them. Let's look at an everyday example to make sure that we understand the concept. A man wandering on the Earth is like a group of tightly coupled kinesins walking on a microtubule. It's a classical particle that we can feel and touch. To stay alive, we continue interacting with a thermal environment called the biosphere. We constantly breathe in and out air, roughly in the order of 10 to the power of 22 molecules per breath. About 70% of our body is made of water. All water molecules get replaced about every 2 weeks. All the atoms inside our body get replaced in a few years. None of the atoms belong to us permanently. At any moment, an enormous amount of atoms join our body, and at the same time, an enormous amount of atoms leave us. Our lifetime is a Sisyphus effort that holds up a ball of interacting atoms against their tendency to disperse. If we examine a particle at great spatial and temporal resolution, we always see a living systems with continuous particle interaction. A particle encapsulates such a living system that produces a packet of distinct actions. In this encircled system, individual kinesins, tubulins, and ATPs are transparent to a distant observer. Kinesins usually walk a few hundred steps along a microtubule, and then fall off. From the perspective of a distant observer equipped only with a Geiger counter, it looks as if particles keep popping into and out of existence in empty space. We can associate each packet with a distinct amount of energy. A particle's energy equals the difference between 2 energy levels when that particle is absorbed or emitted by the system. For example, When a particle corresponding to the 3 yellow flashes is absorbed, the system jumps from E2 to E5. Therefore, delta E, the energy associated with the yellow particle, equals E5 minus E2. Substitute E5 and E2 with the generalized formula above. Delta E equals N5h over tau minus N2h over tau. Combine the common term h over tau. Delta E equals delta N times h over tau. Rearrange the terms on the right side. Delta E equals constant action h times delta N over tau. Delta N over tau is the temporal density of ADP radiation, or the frequency of actions. Let the Greek letter nu denote the frequency. A particle's energy delta E equals constant action h times frequency nu. Nu is the number of actions executed per unit time tau. We arrive at the same formula proposed by Einstein to explain the photoelectric effect. The only difference is the definition of the unit action h. In the universe of photons, h stands for the Planck constant, the base unit of particle interaction that creates the phenomenon of light. In the universe of photons, h stands for the Planck constant, the base unit of particle interaction that creates the phenomenon of light. A photon is analogous to a packet of actions executed by a group of tightly coupled walking kinesins. A beam of light is analogous to a swarm of action packets moving along a path. This formula, together with Einstein's theory of relativity, is the foundation of modern physics. They revolutionize our understanding of space, time, and how our universe operates. However, the foundation of physics has made no real progress since the mid-1970s. The 2 pillars of modern physics, quantum mechanics and general relativity, remain incompatible. Quantum mechanics depicts a discrete and probabilistic universe at a tiny scale. General relativity portrays a smooth and deterministic universe at a large scale. Human physicists happen to live in the middle. They're busy building more powerful particle accelerator and telescope, as if the ultimate laws of the universe could hide only in remote systems far away from the observers. They turn a blind eye to what happens around and inside themselves, as if their own behaviors were not governed by the same laws. The status quo must change. It's long overdue for physics to expand its foundation and try something radically different. We hold these truths to be self-evident, that all particles are created equal, that particles are defined by the action that creates them, that the fundamental laws of physics, when expressed in the natural units derived from the unit action h, shall look identical to all particles, and that any law, if true and fundamental, shall be observed by all particles equally. The principle expressed here is called super-general relativity. When Feynman taught quantum mechanics at Caltech, he told his students that no one has found any machinery behind the law of quantum mechanics, that no one can explain any more than he has just explained, and that no one will give them any deeper representation of the situation. Surely, Mr. Feynman must be joking. If the rule of quantum mechanics can be followed by a mindless particle such as a photon, it must be simple enough for a smart guy such as Feynman to comprehend. We just need to look at the world from the perspective of a short-sighted particle, and not from the perspective of an overthinking theoretical physicist. We're going to deduce the laws of physics from the principle of super-general relativity. The fundamental laws of physics should tell us how our brain works, and how consciousness arises spontaneously from random particle interaction on the membrane of a neural network like our brain. Our journey starts with the derivation of a wave function that governs the motion of walking kinesins. As you might already guess, it has the same form as the rule governing the motion of elementary particles. I hope it will be an intellectually stimulating journey worthy of your time. If you find the content in this channel is interesting, please click the like button below, subscribe, and share it with your friends. It will help to connect those who are also interested in the topic. Thank you very much for your help.